Hi children, hope you are fine. Yeah, good. Let me introduce myself. I am Arun Kumar MS. I am chemistry teacher in Sainik school Kazhakootam. Today I am here to take you to the world of chemistry. I know after hearing the word chemistry, at least some of you are thinking what this sir is going to do, right? Don't worry, I am going to take you to the world of chemistry. And it is very fun, and if you learn chemistry with fun, you will never forget chemistry, right. So, today I am going to take you to a small trip. Are you ready to come along with me for a small trip? Are you ready? Shall we go? Yes. Wait, 1 second. Let me apply a little perfume, okay. Fantastic smell, right? Okay, now we will go. Come, I am going to take you to some places. You have to observe these and just make a note on your book. What all the things that you are going to see, just write down in your note, okay. Oh, what a pleasant scene, right? What you can see there? It's a beach, right? See, after seeing this beach, I remember my first grade teacher who taught me, children, see, sea water is salty, right? I think you might also learn like this, right? Okay, come, shall we go to the next place? Wow, what a fantastic scene. See, you can find waterfall, and this water is constituting the formation of a river, is it? And it is flowing down, and what a fantastic scenery it is, right? Okay, come with me, I will show you another. Wow, what is it? It is an aquarium, right? You can see an aquarium, and there is some gas bubbling in the water, right? Okay, no, it is not going to finish. Come, shall we go? Shall we go? Yes, come. Oh, what this gentleman is doing there? Please look at it, what this gentleman is doing. Oh my God, I think he is spraying pesticides, right? I know use of pesticide is not that much good, but still then he has to do it, otherwise his crops will be totally eaten up by the pest, right? Okay, anyhow, let him carry on. We will continue our journey. Come. My God, I think you can see lot of poisonous gases coming out from the chimney of the factory, right? I think it is really polluting our environment. What to do? We have to run factories also, right? Come. Now, I really fed up seeing all these things. I think I am going back. Are you coming with me? Yes, come with me. Now, I think the petrol in my car is about to finish. Now, we will en route, we will go to a petrol pump and fill petrol in my car. Come. Okay. Now, I think it is enough, right? We will go back. But I feel very thirsty. I want to drink a cup of tea. So, I am going to have a cup of black tea. Do you want anything? If you want, you can choose your drink. I have soda with me, and I have some soft drinks. You can choose any of these drinks. Okay? Children, now let us go back to our class. So, I hope you have written all these things that we saw in our journey in your book, right? Yes. Now, let me ask you, can you find some common features in what all the things that we saw? Can anybody, any guess? Yeah, you can try it. Let you give a wildest guess, no problem. Yes, try it. Yeah, I could hear somebody saying something. Yes, tell it. Tell it. What? Solution? Yes, right, you told it rightly. So, what we see around us are mainly solution. They are not pure substance, they have two or more substance mixed together, right? So, today I am going to take you to the world of solutions. So, before you learn the concept of solution, don't think that you are going to learn something for your marks. It is above that you are going to study something that is applied in your day-to-day life. I will show you certain examples for it. Please wait, okay? Have you seen this? You can see a mountaineer who is carrying some oxygen cylinder. Particularly when he goes to higher altitude, he has to carry it, otherwise he will feel difficulty in his breathing, right? It is not only applicable for mountaineers, it is equally applicable for scuba divers. So, this scuba divers, they carry oxygen cylinders with them, which is also an application of solution. We will see what are these applications in detail when we go further in our syllabus, okay. Now, you can see the pruny hands. It is quite often seen, particularly when you handle with soap or soapy water, or you immerse your finger in water for a long time, right. It is again some application of solution you will find in it. Then the plants which were not watered for few days or 1 or 2 days get wilted fast, is it? And you will see after watering that plant, it get revived. So, you can see that. And it is very common experience that when we boil water, some vapors comes out from it, right. So, again you can find the application of solution in it. When you are sick, you go to doctor, doctors may give you injection, right. And the medicines that you are using, what is it? It is again a solution, okay. Now, it is a very common scene, particularly in a European country, where the roads get filled with snow during winter season. How to remove this much snow from the road? The transportation becomes very difficult. For that, we apply the concept of solution. So, these are actually what we are going to discuss in our chapter, solution. So, shall we go? So, here we go. Okay. Now, we will discuss about mixtures. You know what are mixtures? Mixtures are two or more components mixed together. I know if I say the word mixture, the first thing that comes in your mind will be definitely the mixture that you eat, right? Can you say why that mixture is called mixture? Yes, it consists of so many components in it, right? It consists of so many components which all these things are eatable. So, that is why it is called mixture. But can you call Nimbu Pani a mixture? Yes or no? Yes, that is also a mixture, it also consists. But there is a difference between these two, right? One, you can easily separate the components which are present in it, and it is easily visible also. Whereas in Nimbu Pani, you have the components, different components, but you cannot see them separately and you cannot separate them by simple methods, right. So, we will be discussing about two types of mixtures. One is homogeneous mixture and another is heterogeneous mixture. Okay. So, what does heterogeneous mixture means? Heterogeneous mixture is a mixture which contain two or more components in it, and these components are chemicals, nothing else chemicals. It can be either element or a compound, and these are visually distinguished. You can easily identify them, as well as you can separate them by some physical means. Okay. Now, let us see what are homogeneous and heterogeneous mixtures, right. See, what is heterogeneous mixture? You can see heterogeneous mixture is a mixture. Okay, it is a mixture of two or more chemical substances. It can be either element or it can be a compound, where the different components can be, you can see it can be visually distinguished and easily separated by some physical method, right. In this picture, I included the naturally occurring form of sulfur, but this sulfur do not exist as free sulfur. Instead, it exists along with some other sulfides, right. So, you can easily identify both sulfur and sulfides together. Then I will show you another example. You consider the case of castor oil and water mixture. You know, oil and water do not mix each other. Will they mix? No, no. So, when you put oil in water, what happens? You can see this, oil always float over water, right. And if you try to test, first you test the composition of this mixture. In the beginning, you will take from the top, from the middle and from the bottom, you will get different constituents. From the top you will get only oil. In the middle you may get, where that layer where it intermix, you may get both oil and water, and at the bottom you will get only water, right. So, this is why we call it as a heterogeneous mixture, right. Next we will go to what are homogeneous mixtures. Homogeneous mixtures are mixtures where two or more components are present in it, and it can be either an element or it can be a compound. It can be either an element or a compound, and these cannot be visually distinguished. That means they form a uniform mixture. You cannot separate them and you cannot identify them by any way, right. But you have to use some other techniques other than the normal simple physical methods. You have to use some other techniques for separating the components, right. See, example, I told about mixture, right, the one which we eat. So, if I put it in a mixer jar and grind it and made into a powder, if I give you, will you be able to separate each of the components from it? No, right. So, that is why I can then call it as a homogeneous mixture. It is not a simple heterogeneous mixture, it is now it has become a homogeneous mixture, right. Another example I will tell you, I have a mixed fruit juice. I think you are familiar with fruit salad, right. You have different fruits cut into small pieces and you put it in a bowl. If I serve you that, you can take whatever you want from it because you can easily segregate them. If you do not like guava, you can separate guava and have the remaining, right. But if I put it in a mixer jar and if I make into a juice, mixed fruit juice, if I give you, will you be able to separate it? No, right. So, that makes the difference between homogeneous and heterogeneous mixture. So, here you will be seeing a solution of sulfur in carbon tetrachloride. Okay. Now, if I add a spoon of sugar into water, what happens? It starts dissolving, right. Now, if I stir it, what you can see there, if I start stirring, it completely dissolves in it. Now, where is the sugar? It vanished. Where it vanished? It went into the intermolecular space between the water molecule. Now, if I add sugar to a cup of tea, right, after mixing, I am giving you a straw, asking you to check the taste of the tea. You just keep at the topmost portion of the tea and have a taste. What you will feel? It will be tasty and you will feel the sweetness. Now, you just little bit down, you keep the straw and taste it. Are you going to get different sweetness? No, right? You will get the same sweetness. Then again you dip little bit down and from the bottom again you get the same taste. That means in homogeneous mixtures it retains its identity as a whole and it remains uniform. Is it okay? That is why we call it as a homogeneous mixture. Now, let us see what is a solution. See, solution is a homogeneous mixture of two or more chemically non-reacting substances whose composition can be varied within certain limits. So, what is a solution? It is a homogeneous mixture of two or more chemically non-reacting substance whose composition can be varied within certain limit. So, if I take alcohol and water, I can mix alcohol and water in any ratio, any proportion. If I take 10 ml of water and 90 ml of alcohol, will it form a mixture? Will it form a clear solution? Will it form a homogeneous mixture? Yes. Similar to that, if I can take reverse 90 and 10, then also it gives. If I take 50-50, then also I get. That means it can have a varying composition within a limit. That is what we call it by the name solution. So, what are solution, children? Solution is a homogeneous mixture of two or more chemically non-reacting substance whose composition can be varied within a limit. Is it clear? Okay. Next we will see what are the different components present in a solution. Now let us see what are the different components present in a solution, right. So if you take a solution, solution basically consisted of a solute and a solvent in it. It consisted of a solute and solvent in it. The substance which is present in larger quantity is called solvent, and the substance which is present in lesser quantity is generally called a solute. So when a solute is dissolved in a solvent, you are going to get what? You are going to get a solution. So we can say solute plus solvent gives what? It gives you solution. Is it clear? Now you can see solutes, particularly if it is a solid, it will be in an aggregated state. Okay, it will be an aggregated state. But when the moment you start dissolving it in a suitable solvent, what happens to it? You can see it disperses, it get dispersed into the medium. Thereby it forms an uniform mixture. It forms uniform homogeneous mixture. Now based on the number of components present in the solution, you can classify solutions into different types. First one is binary solution. Binary solution. What do you mean by binary solution? If you have only two components, that is one solute and one solvent, you call it as a binary solution. That means only one solute and one solvent, right. Now if you have more than two components in it, then it is called if three components are there, that is two solute, one solvent, two solute and one solvent, then you can call it as ternary solution. And if you have more than three components present in it, you can call it as multinary solution. So we can classify solutions basically into three based on the number of components present in it, right. If only two components are there, what you call? You will call it as binary, that is one solute and one solvent. Then if it contain three, you call it as ternary, okay. And if there are more than three, what you call? You will call it as a multinary solution, right. Next, again you can classify solution on the basis of the phases of the solute and solvent present in the solution. In this session, we will be focusing mainly on binary solution. We will be focusing primarily on binary solution, right. Now we will further classify this binary solution on the basis of the phases of solute and the solvent. Now let us see. So you can have a solute and solvent in a solution. Solute and solvent can be either solid, liquid or gas, right. Now what is present in major component? Which is the major component? That is the solvent. So usually solvents decides the phase of the solution, how the solution look like. It is actually decided by the phase of the solvent, right. So on the basis of the phases of the solute and solvent, we can further classify solutions into different types. So we have gaseous solution, then liquid solution and solid solutions, right. Gaseous solution, liquid solution and solid solution. See, the appearance of a solution is primarily decided by the phase of the solvent because it is larger excess. So on the basis of that, we can say, see, in gaseous solution you have the solvent in the form of a gas, right, and what would be the solute? It can be anything like solid, liquid or gas, but the solvent will be always a gas, right. So first we will see a solid solute in a gaseous solvent, a solid solute in gaseous solvent. Can you give an example for it? Yes, camphor in nitrogen is an example for a solid in gas. You know, camphor is a solid which is easily sublimable and it sublimes and comes into the vapor and get mixed with gas. So, here you can see camphor in nitrogen is an example for this type of solution. Next one is a liquid in gas type, a liquid in gas type. Can you give an example for it? Okay, you can see chloroform mixed with nitrogen gas. Again, you know, chloroform is a liquid and it evaporates and it get mixed with nitrogen gas. That is an example for a liquid in gaseous type solution. And the next one is a gas in gas. See, we are living in a gaseous envelope, right? In our atmosphere, a large number of gases are mixed together, primarily nitrogen and oxygen. So, you can say the same as the example for a gaseous solution where gas is the solute and gas itself is the solvent. So, you have a mixture of oxygen and nitrogen as an example for this. Next, what is the next stage? That is a liquid solution. Is it liquid solution? In liquid solution, what should be the major component? Then only it can appear like a liquid. What would be? It would be solvent would be liquid. Good. So, we can say the solvent is a liquid. So, all the case you have liquids, liquid, right. Now, shall we add solute to it? Okay, we can add a solid solute to a liquid solvent, solid solute to a liquid solvent. This is the most common thing that we always do in our home. We either add salt to curry or we add sugar to tea, is it? When you make nimbu pani, we add sugar to it. All these are solid. The solid when dissolved in water, it forms a solid in liquid type solution. And give an example, all these are examples, right. So, we can say glucose dissolved in water is an example for a solid in liquid type solution. Next one, you can liquid in liquid, that is a liquid can be dissolved in another liquid, example alcohol and water. You can mix alcohol and water, you can get a solution of alcohol in water, right. Similarly, you can mix carbon tetrachloride and chloroform, both are liquids, you can mix them and you get a solution, right. So, example is ethanol dissolved in water is an example for a what? Liquid in liquid type solution. Next one is a gas dissolved in liquid. In the beginning when we went for the trip, I show you an aquarium where some air is passing through that water, right. Here comes that, what is it? The oxygen in the air is dissolved in water, for that it get oxygen supply for the aquatic animals, right. So, you can say oxygen dissolved in water is an example for a gas in liquid type solution. Happy? Okay, we will continue. Now, solid in solid solution, right. So, since it is solid solution, the chief component, that is the solvent, will be a solid. So, I can fill here solid, solid and a solid, right. Now, can I add a solid to another solid? Is it possible? Think? Yes, you can add. Alloys are example for it, isn't it? So, the gold ornaments that we purchase from the jewelry is not pure gold, it is a blend of copper and gold. It is an alloy of a copper and gold, right. So, that is an example for copper dissolved in gold is an example for a solid in solid type solution. Next one is a liquid in solid type. Okay, liquid in solid type, a liquid can be dissolved in a solid. Example amalgam. Okay, you take mercury and amalgamate it with sodium. So, you can have amalgam of mercury with sodium is another example for what we call a liquid in solid type. And the last type is a gas in solid. Gas in solid. Any idea? Anything coming to your mind? No? I will tell you. Okay, you have hydrogen gas when it is heated in palladium metal. There are large number of intermolecular space, what you call it as interstitial voids, and into this interstitial voids of the palladium atom in the solid, it can absorb hydrogen and keep inside it. So, merely it look like simple palladium, but if you go deep into it, you will see the hydrogen atom hiding inside a palladium metal, right. So, that is an example for solution of a what? A gas in solid, that is solution of hydrogen palladium. Is it okay? Shall we continue? Yes, good. Now, we will be discussing on the methods to express concentration of the solution. See, it is a very simple thing, method to express concentration of the solution. See, I have a cup of tea to which I add 1 spoon of sugar, and the same cup of tea I am adding 2 spoons of sugar to it. Which one will taste more sweeter? Obviously 2 spoons, right. So, I can tell first one is having lesser quantity of sugar in it, second one is having more quantity of sugar in it. So, can I say first one is a dilute solution and the second one is a concentrated solution? Can we say? The same thing we will be looking at. So, what I just told now is only a relative concept. It is only a qualitative method. It is not a quantitative, it is only a qualitative method. But now the concept of adding sugar varies from one case to another case, right. So, now I am continuing with the same example. If I take one more cup of tea and adding 1 spoon of sugar. So, now I have 3 conditions: 1 cup of tea with 1 spoon, second cup of tea with 2 spoons and third cup of tea with 3 spoons. Now, with respect to the first one, the second one is concentrated, right. But the same second one, if you compare with the third one, it became dilute. So, is it a standard method to express the concentration? No, right. It can be varied, okay. But it is one of the methods by which you can express the concentration of a solution, right. So, here you see I have 3 beakers with equal quantity of water in it, right. To the first one I am adding around 5 gram of copper sulphate, okay. 5 gram of copper sulphate I am adding to it. In second case I am going to add 10 gram of copper sulphate, okay. And in the third case I am going to add 30 gram of copper sulphate to it. So, what visible change you can see in it? In first case, when you add limited, that is 5 gram, only less, 5 gram of copper sulphate when you add, the solution becomes somewhat bluish in color and it is pale blue in color, right. Now, in second case I added 10 gram, so the concentration or the amount of the copper sulphate in the solution is much higher when compared to the first one, right. So, I can call the second one is a concentrated solution. Now, what happen if I add excess 30 gram? If I add 30 gram, what happen? You will be able to identify the solution become deep blue, right, no doubt. But at the same time you will be able to see some amount of copper sulphate remains insoluble. It cannot go further into the solvent. What you call such solution? You can call such solutions as saturated solution. What do you call? You call as saturated solution, right. Now, you take a simple case. Okay, for example, I am taking a beaker, right. I am taking one beaker. In that beaker, I am adding 100 gram of sodium acetate, CH3COONA is the formula of sodium acetate. It is highly soluble in water, right. So, I kept at room temperature 25 degrees Celsius. At 25 degrees Celsius, I took some quantity of water I took, then I added 100 gram of sodium acetate to it. So, when I add sodium acetate, initially I see only lesser amount of sodium acetate start dissolving, right. But if I keep stirring, I can ensure more and more amount of sodium acetate dissolves in it. And finally, at 25 degrees Celsius, the same temperature, I could see nearly 91 gram of sodium acetate dissolved, right. And 9 gram of that remains insoluble, 9 gram of that solid material remains, right. So, if you try stirring, no use, it always remains that. So, what you have made right now, can you tell? You have prepared a saturated solution of sodium acetate in water at 25 degrees Celsius. Is it okay? Condition clear? Now what I am going to do? I am going to increase the temperature from 25 to 50. Okay, I am going to increase the temperature from 25 to 50 degrees Celsius, right. So, the moment I increase the temperature, what I could see is there remains 9 gram of solid sodium acetate, right. What happened to that 9 gram of sodium acetate? Is it still there? No, it vanished. Where it went? It further dissolves in it, right. Are you agreeing? It further dissolves in it. So, the saturated solution which you prepared at 25 degrees Celsius now became unsaturated. Now it became unsaturated, right. It became unsaturated at 50 degrees Celsius. So, now at 50 degrees Celsius the solution which was saturated at 25 degree now became unsaturated. Is it okay? Next, what I am going to do? I am going to keep the solution and letting it to cool down. So, I am letting it to cool down. So, as the temperature slowly comes down, the solution will remain solution, right. So, slowly the temperature falls down and come back to the normal room temperature. Okay. What was the initial amount of solute that dissolved at 25 degrees Celsius to form the saturated solution? Was it 91? Was it 91 gram? Okay. But now you look at this. When the temperature is brought back to 25 degrees Celsius from 50 degrees Celsius, the amount of the solute that is dissolved in the same quantity of solvent still remains same. What is it? 100 gram, or shall I tell 9 gram excess it dissolved in it. Can I say so? 9 gram is excess. So, what do you call that excess amount that dissolves in it? Now, can you call that solution as above saturation? What do you call? You call it as super saturation. Can we call it as super saturation? So, that solution is what we call it as super saturated solution, right. Now, do you think it is stable? Is it going to be stable? No, it is no longer stable. Why it is no longer stable means it always can accommodate only 91 gram of solute in that quantity of solvent at 25 degrees Celsius, right. But it is having some excess amount in it. That excess amount will have a natural tendency to come out of the solution and come back to the crystalline form, right. It come back to the crystalline form. So, you will see that if you try to bring any small kind of disturbance to that system, it definitely try to come back to the original dynamic equilibrium. So, if you put a small piece of or a small grain of this sodium acetate to it, you will be able to see it immediately crystallize. Okay, the excess amount, that 9 gram is excess, right. That 9 gram of a sodium acetate immediately crystallize. Okay. So, let us see, you can see the same thing here, the crystallization of this. What is this? This is a very simple experiment that we quite often do in our lab. This is called hot ice experiment. Okay, hot ice experiment. And this is nothing but the sodium acetate, you prepared a saturated solution, further you increase the temperature and make it supersaturation. After attaining supersaturation, you cool it, bring back to the room temperature, still you find a solution as it is. Now you put a small grain of what you call sodium acetate to it, or you simply you shake it, that is enough. It immediately come back to the normal state and it gives out all the excess amount of a sodium acetate which it took. Is it clear? Okay. Next, we will go to the solubility curve. The same thing I can explain with the help of this solubility curve. You can see I have plotted the amount of solute in grams per 100 gram of water, and it is plotted against the temperature. It is plotted against a temperature. Now, you look at this. At each temperature, you will have a saturation point, that is the amount of solute that could be dissolved in a particular solvent remains constant, right. So, you find that and you can plot a graph. You can see you plotted a graph, right. and at this point at any particular temperature, that is the maximum amount of solute that you can dissolve. Now you take a temperature T1, what is its maximum solubility? What is the maximum solubility at temperature T1? It is this one, are you agreeing? This is the maximum solubility. Now I am increasing the temperature from T1 to T2. So I have only this much amount dissolved, right? But further I can add little more. To what extent I can add? I can add up to this much more I can add. Okay. Now what I got is a saturated solution of this. Clear? Now I am going to decrease the temperature from T2 to T1. I am going to decrease the temperature from T2 to T1. So if I decrease the temperature from T1 to T2, the amount of the solute that is present excess, that is this much is excess, right? That will still remain in the solution. It is not going to come out. It remains in the solution. But as the temperature decreases, what you see, this much excess solute is present in the solution. That is why we call this as a supersaturated solution. Now if you try to disturb this system, it immediately come back to its original equilibrium by crystallizing this much extra salt which already it took at the same temperature. Is it clear? So this is the solubility curve. Next we will be discussing about the quantitative method for expressing the concentration of the solution. Quantitative method. Let us see one by one. The first one is mass percentage, or it is denoted by W by W, mass percentage. See, it is merely percentage. Okay, you know how to calculate percentage, right? The same concept we are going to apply here. I can write mass percentage is equal to what? Mass of solute divided by mass of solution. Mass of solute by total mass of solution into 100. Simple, right? Total, out of that total, how much component is present? That is what we call. If you take 100 parts, in that 100 parts of that solution, how many parts of a solute is there? That is what we mean by what? Mass percentage. Now let us see one example. Find the mass percentage of 5 gram sodium carbonate dissolved in 50 gram of water. Can you try it? Read the question once more. Find the mass percentage. You are asked to find the mass percentage of 5 gram of sodium carbonate dissolved in 50 gram of water. So what is the mass of solute? Which is the solute here? Mass of solute is equal to 5 gram. Are you agreeing? It is 5 gram. Now what is the mass of solvent? It is not solution, it is mentioned 50 gram of water. So mass of solvent is equal to, what is the mass of solvent? 50 gram. So what is the total mass of the solution? Can anyone say? Yes, good. That is 55. Total mass of solution is equal to 55 gram. Okay, now can we find what is the mass percentage? So mass percentage, that is mass percentage of the solution is equal to what? Mass of solute. What is mass of solute? That is 5 divided by what is the mass of the solution? Total mass of solution is 55 into 100, right? That is, you can write it as 0.9 percentage. Okay, sorry, 0.09 percentage. So this is the mass percentage of a sodium carbonate in 50 gram of water. Is it clear? Okay. Okay, we will be discussing the next one, that is oleum percentage. So what is oleum percentage? Again it is percentage. So you can say oleum percentage is equal to volume of solute is equal to volume of solute divided by total volume of solution into 100. And this kind of units commonly we express particularly when you have two components liquids, that is alcohol in water. Okay. So in those kind of examples or cases, we can use this method to express the concentration, that is volume percentage. What is it? It is the volume of solute upon the volume of solution into 100, right. So, we will see one example for it. See, can you read this question? A solution is prepared by dissolving 90 ml of hydrogen peroxide in enough water to make 3000 ml of solution. Identify the concentration of hydrogen peroxide. So, what is the question? Read it once more. A solution is prepared by dissolving 90 ml of hydrogen peroxide. So, 90 ml hydrogen peroxide is nothing but the volume of the solute. So, I can write volume of solute, how much, is equal to 90 ml. Okay. And it is made into a solution by adding sufficient quantity of water, so that the final volume of the solution, so the total volume of solution is how much? Volume of solution is equal to 3000 ml, right. And you are asked to find the concentration of the hydrogen peroxide, that is you are asked to express it in terms of volume by volume percentage. You can directly do it. What is it? Volume percentage of hydrogen peroxide is equal to, volume of hydrogen peroxide is 90 divided by, what is the volume of the solution? 3000, okay, into 100. Out of 100 you have to find, is it? So, it comes around 3% volume. So, we write 3% V by V. Is it clear? Okay. Which is the next one? We will see. The next one is mass by volume percentage. Mass by volume percentage. So, this kind of expression is commonly done when the solute is a solid and the solvent is a liquid. When the solute is a solid and the solvent is a liquid, we use this method. So, what is it? Again it is percentage. So, you can write what? Mass of solute divided by volume of total volume of solution into 100. Okay. So, that means if you take 100 parts of the solution, how many parts of or how much mass of a solute is dissolved in it? It is commonly used for expressing the strength of solution. Okay. Now, let us see one more example. See, 2 liters of an aqueous solution of potassium chloride contains 45 gram of potassium chloride in it. What is the weight by volume percentage concentration of this solution in gram per 100 ml? So, what you are asked to find is, you have to find, if you take 100 ml of that solution, how much gram of the solute, that is potassium chloride, is dissolved in it. Simple, right? So, what is the volume of the solution? Volume of solution is 2 liters. So, you can write volume of solution is equal to 2 liters, but you are asked to find in terms of milliliter. So, you can convert it into milliliter. Is it okay? Yes. Next, what you have given? A solution of potassium chloride contain 45.0 gram, that is mass of solute is given. Mass of solute is equal to 45.0 gram, right? And you can directly find it, nothing else. What is it? Mass by volume percentage, that is W by V is equal to, what is it? It is 45 divided by 2000. Now, 45 upon 2000 give you per 1 ml, agree? Now, you have to find it for 100 ml. So, what you will do? Into 100, right? So, you will be getting around 2.25%. 2.25%, right. So, children, we will be winding up this session with this. In the next section, we will be continuing with the remaining methods to express the concentration of the solution and the solubility of various solutes in different solvents. Okay, thank you.